Okay, let's go over these problems from the textbook you're supposed to do over the weekend. Okay, numbers 23 and 25, there is no calculus involved whatsoever. It's just a review of those properties of logs that can be used in calculus to make differentiation easier. And so for 23, actually I'm going to rewrite the properties over here. So the natural log of a times b is the natural log a. That is crap writing, but I'm doing this kind of quickly. Natural log of b. The natural log of a divided by b would be the natural log of a minus the natural log of b, and the natural log of a to the b power would be b times the natural log of a. And when you try to use that property, just make sure you recognize that the exponent is on the argument of the log and it's not the entire logarithm being raised to a power. So, number 23, notice that I have x times y in the numerator, and then I am dividing by a z. And the shortcut that I remember, or the method I remember, is that anything in the numerator is a positive log. So I have the ln of x plus the natural log of y, and then I'm dividing by the natural log of z. And so that is how that one will split up. If I did have something like the natural log of x over y times, not y times y, y times z, in that case, that would be the natural log of x. That's in the numerator, so that's a positive log. Y and z are both in the denominator, so you would make those negative. So minus natural log of y and minus natural log of z, because you are dividing by a z. A lot of people see y times z and think that you need to add those two, but think of it as natural log of x, and then you're dividing by both the y and the z, so we subtract both of those. Number 25, it is a product, so that would be the natural log of x plus the natural log of the square root of that stuff. But do remember, a square root is the same thing as an exponent of 1/2. And so when I write it as an exponent, I can then take this exponent, bring it down in the front, and I'm left with the natural log of x plus 1/2 natural log of x squared plus 5. And that's all you have to do for the first two. We'll use those properties later in some of the differentiation problems, which start with number 47. So here we are actually finding the derivatives, and for the derivative of a log, number 47 is going to be really easy, because if you remember the derivative of a natural log, you simply put the argument, in this case that would be 3x in the denominator, and the derivative of that in the numerator. In this case the 3's do cancel, leaving you with just 1 over x. Number 51 starts the more difficult ones, because now I have something else going on, and this one is the entire logarithm to the 4th power. This is not the same as the natural log of x to the 4th. So I cannot pull that 4 down as a property of logs, but what I do have here is a chain rule where I have stuff being raised to the 4th power. So the first thing I'm going to do as a chain rule is I'm going to bring that 4 down, and I'm doing the derivative of this as if it were saying just x to the 4th. The derivative of x to the 4th is 4x cubed, only this time in the place of an x, I have a natural log x, so this is a chain rule. Then once I do the derivative of stuff to the 4th, I then multiply that by the derivative of the inside, which is 1 over x. So your entire derivative for number 51 is 4 natural log x cubed times 1 over x. 53, this one now, notice they didn't put the entire log in parentheses. This is the argument being squared, so I can actually pull that 2 down as a property of logs. This is not a calculus maneuver. I'm just using properties of logs. I'm taking that 2 and moving it to the front. And when I do that, I make my derivative significantly easier, because now I can do the derivative of just the natural log of t plus 1, and I can just leave the 2 on the outside. So this derivative, y prime, I'm going to leave the 2, and then the derivative of the natural log of t plus 1, you put the t plus 1 in the denominator, and the derivative of that in the numerator, and there is your answer. I very frequently use Leibniz notation, so in this case, because y is a function of t, it would be dy dt, not dy dx. Just a little side note there. 57, again, it looks really ugly on the surface, but you can use those properties of logs. It is x divided by x squared plus 1. I'm not going to do a quotient rule. I'm not going to dive straight into the calculus. I'm going to start by doing the natural log of x minus the natural log of the denominator. And in using that property of logs that you learned in pre-cal, I now have an easier derivative, because I no longer have a chain slash quotient thing going on. The derivative of natural log x is 1 over x minus the derivative of natural log of x squared plus 1 the x squared plus 1 goes on bottom, and the derivative of that goes on top, and you're done. Significantly easier than doing the quotient rule. Number 70, I assigned because I have not talked about the role of absolute values when doing natural log derivatives, but it turns out that they don't really have a role. You can use the same derivative technique. So the derivative of the natural log of cosecant x, if it's in absolute values, doesn't really matter. That answer is going to be the negative. Whoops, I'm going to do this the way I've been doing it earlier. You put the inside on bottom, so the cosecant of x goes in the denominator. The derivative of that, which is negative cosecant x cotan x, goes on top. And in this case, when simplifying is convenient, like it was in number 47 up here, where I canceled the 3, I'm going to do the same thing right here. I can cancel out these cosecant x's, and your answer is just the negative cotangent of x. And there's your answer for number 70. And then the last problem is using the derivative to answer a bigger question, and we want the equation of a tangent line. And the equation of a tangent, anytime you see that phrase, you should immediately think point and slope. You will always need those two pieces of information to write the equation of a line. Well, this one, the point, is painfully obvious because it is explicitly given to you, but do know that if they did not give you that 3 and they only gave you that x was 1, then you could plug 1 in, and it turns out that f of 1 is 3 times 1 squared minus the natural log of 1, and you should know that the natural log of 1 is 0, and so that does give you a y-coordinate of 3, as they told you already. The slope comes from the derivative, so I'm going to get my slope by first finding the derivative of this function, which will be 6x, and the derivative of natural log x is 1 over x, and now I plug my x-coordinate into that, my x-coordinate of 1, to get my numeric slope. So 6 times 1 minus 1 over 1 gives me a slope of 5. And once you have your point and your slope, you can take both of those pieces of information and roll them into point slope form, which will be y minus 3 equals my slope of 5, x minus 1, and you are done. There's no need to turn that into point slope intercept form or anything else, unless I force you to put in the instructions or something like that. So there are the homework problems from page 331. You also had homework problems from another textbook, page 137, but we covered almost all of those in class on Friday, so I'm not going to do those in a video.